And I called this the best of both worlds to the consternation of all my reviewers who said, why don't you add a subtitle? Because it's about combining two of my favorite things in programming, right? And the first of my favorite things you're not going to find very surprising, given this is the International Conference on Functional Programming, and that's functional programming. But in particular, I'm thinking about sort of polymorphic combinator programming, the fact that we can define ideas like functor maps, like the monadic bind operator, even like composition in a generic way and reuse it in the process of defining more interesting abstractions before eventually getting to our programs. And the second thing won't be terribly surprising if you look at the talks bracketing this one, and that's cake. But I don't mean a specific instance of cake with candles and icing and compilers. I mean the abstraction of cake, right? Once we sort of abstract away the icing and abstract away the candles and abstract away the flavor, what we have left is that cake is that which you cannot both have and eat. And from that perspective, we can recognize that programming is full of cakes, right? Whether it's file handles that you can't read from after they're closed, whether it's operating system capabilities that can be assigned to this process or that process, or whether it's arrays that have to be sort of, updated in a linear fashion to preserve their semantics. This idea sort of pervades a lot of common programming problems. Some people would call these things linear types. And in fact, the observation that linear types allow you to capture these things is not new. It's been made over 25 years ago. And so one might ask, well, if we have all these problems that can be solved by linear types, and we have all these people who are interested in complicated, fun type systems that capture interesting invariants, why are we not all writing programs in linear functional languages? Right? Somebody's very angry that I'm not talking about clean, but I'll get back to that. So I was interested in that question as well, and I tried to figure out what goes wrong if we just put linear types and functional programming together and see what happens. And so I want to show you a simple example. Right? This is the second simplest polymorphic function I know. It's the k combinator. And let's talk about what happens if we look at the k combinator in a linear context. Right? Well, the arguments are easy. We use x once, we use y no times. So x can take on arbitrary values. It could be a Boolean, it could be a string, it could be a file handle. Y can't take on linear values. Right? So we can have Booleans, we can have strings, but we'd best not have session-typed channels. But that's not quite all we need to talk about, right? Because the first thing that happens with this is we're going to apply this to some x, and we're going to get pause for effect. We're going to get this term back. So the question is this subterm linear or unrestricted? Is it fair for us to copy this subterm? And when we do so, will we break any of the safety properties we were trying to enforce with linearity? Of course, the answer is that it depends on x. Right? If we started out by instantiating x to something like file handles, then this is going to be a closure containing a file handle. And if we copy the closure, we're going to have to copy the file handle inside it, and we're going to violate the safety properties that we wanted to maintain. On the other hand, if we choose x to be, say, Booleans, and then we have a closure with, say, true inside. And I think it'd probably be a little disappointing if I were to come along and tell you you're no longer allowed to copy functions that capture true. It would be very disappointing. So in essence, we have a sort of problem that it depends, right? And I'm going to sort of write that this way, although this is a bit informal for now. If all we know is that u is unrestricted, which I'm going to abbreviate un, well, then we have a function to which we give a t and we give a u, and we're then going to get back a linear function, a function that we can't copy or duplicate. And I'm going to indicate that with this sort of empty circle next to the arrow. On the other hand, if I know that both t and u are unlimited, right, so t is a Boolean, then after applying it to t, I'm going to get back a function that I can copy. And my point here is to say these are not the same type, right? We have sort of types distinguishing when functions, they're not the same type, and it doesn't depend in general on u and t. Right? In this case, it depends on t, it doesn't depend on u. But the problem is not the arguments of the function, the problem is not the return value of the function, the problem is what the function's captured, the closure. Right? So we're sort of going to need to have distinct function types. Or function types that distinguish when functions can be copied and when they can't, when they've captured linear things and when they haven't. So then we get to our problem. How do we do generic combinator programming with these sort of multiple function types? The crux of the argument is basically to say I don't want to have to repeat myself. I don't want to have two definitions of the k combinator. But I think it's worse than that in a way, because all of the things that make functional programming beautiful, whether it's our maps and filters, whether it's compose, whether it's bind, these are all things that operate on functions and all things that operate in a polymorphic fashion. And so this problem of having combinators with multiple types is going to pervade the core of what makes functional programming attractive. My argument is that this is a big part of why we're not all writing in linear functional languages today. So what can we do? Well, I want to introduce a thing called that I call qualified linear language, or quill. The idea is to integrate linear and polymorphic functional programming using predicates on types. I'm going to show you that we have I'm going to claim that we have principal types and decidable type inference, and I'm going to say that this is a conservative extension of existing functional languages. This is going to build on some recent work, particularly by Mazurak et al. And Tav and Pucella. And again, the crucial thing that's new in this calculus is going to be the treatment of functions, right? But some of you are saying, I've heard this word qualified before, and qualified has to do with overloading, right? Why are we talking about overloading? So I want to start with a simple example. So here's a function that doubles its argument, right? And what do we know about the type of x? Well, we know that it has to be numeric so that we can add it. And we know that it has to be unrestricted, not linear, because I'm going to use it twice. Now, from a particular perspective like mine, we know how to characterize that first thing of being numeric, right? We want to introduce some sort of type class or qualified type that says, well, x can be instantiated to arbitrary types so long as they're numeric. Can we do something similar for unrestrictedness? Can we characterize unrestrictedness by the sort of operations that we can do on unrestricted values, right? So let's try to write this a little more explicitly. Instead of just using x twice, I'm going to introduce an operator which allows me to duplicate values, right? So dup x here is going to return me two values, which I certainly hope are equal to x. I'll call them y and z, and then I can add y and z. Now I have a term that follows a nice linear typing discipline. I only use each argument once. And I figured out the sorts of operations that are going to characterize unrestricted types. Just as we could characterize numeric types by the use of plus, we can characterize unrestricted types by the use of these operators duplicate and drop, right? This corresponds to sort of some work on the interpretation of the exponentials by Filinsky and Seeley. And if I take this approach of sort of saying, well, I have some class that's going to contain these dup and drop operators, I can now compute a type for my doubling operator. It's going to say, given that t is numeric and given that t is unlimited, I can take a t and give you back a t unrestricted, right? Now, of course, I don't actually want to write the code at the top of the slide, right? I don't want to have to write in terms of dup and drop. So what we do in quill is to say, well, you can use the same, reuse variables, and the introduction of these dup and drop operators will be sort of implied by the usage pattern of variables, right? Okay, so I think this is cool. It's actually been done before by Gan et al. But it hasn't gotten to the problem I actually started with, which is the treatment of functions, right? So how do we get from here to a treatment of functions? And for that, I want to start with an application, specifically uncurried application. So again, thank you. Again, the linearity of the arguments isn't terribly exciting here. We get an f, we get an x, we use an f, we use an x, and that's fine. But remember what I said about needing two different types of functions. And they're both things that we can abstract to create, and they're both things that we can apply. So in this case, we know that f could be the linear function space. We're not duplicating f. But it doesn't have to be the linear function space. It could be the unrestricted function space just as well. We wouldn't be violating any safety properties. Nothing would go wrong if we stuck an unrestricted function in for f, right? In fact, something would go wrong if we had to sort of duplicate our application operator and everything else that sort of abstracts over a function to have one version for unrestricted arguments and one version for linear arguments. The way I want to look at this is to say, in essence, in this calculus where we have sort of multiple function types, we want to overload application, right? Space is kind of overloaded so that its left-hand argument can be either unrestricted or a linear function. So I'm going to introduce a class called fun that captures functions. I'm actually not going to introduce a class because classes have methods and methods are applied, and I'm trying to define what application means. But I'm going to introduce a qualifier called fun, which ranges over function types. And so what I'm going to say is that the type of this application operator sort of says, well, for any function type f, if you give me an f from t to u and a t, I'll give you back a u. Now, I don't want to sort of have to always write this stuff in prefix notation. So I've got a bit of syntactic sugar on the side. When I write t arrow fu, that means ftu, but under the constraint that f is a function. And similarly, when I just write t arrow u, that means the same thing, but for some fresh f, right? And so now I have a nice type for my application operator that accounts for both linear and unrestricted functions. But now let's look at another application, that one. So the story for f and x is the same, and we know that f needs to be in the fun class, or have the fun constraint, and we know that x is an argument. But now we sort of have the problem that I started with. Consider this subterm, right? The linearity of this subterm depends on what it's captured. It's captured f. If we give application here a restricted, linear f, then this subterm also has to be linear, or else, we could copy it to copy the f that it's captured. On the other hand, if we give it an unrestricted f, then we don't want this captured thing to be linear, right? We'd like it to be just as useful as it is in sort of typical functional programming. So I sort of said the linearity of the partial application, again, depends on the type of v. If I sort of try to write out the valid types of this thing, there are a few of them. But the key point is to say there's a relationship between the linearity of the argument, the first argument, the TDU function, and the linearity of the resulting closure that I build, the second TDU function. If the thing that comes in is linear, the thing that comes out had best be linear. If the thing that comes in is unrestricted, the thing that comes out can be unrestricted. But of course, it doesn't have to be. I could construct a linear function just as well. Again, if you're looking at this through the sort of lens of overloading, we can imagine that what's going on is that the second lambda here, lambda x, is kind of overloaded. It's constructing whatever function space is appropriate for the values it's captured. If that lambda has captured a linear function, it's going to construct for us a linear function. If it's captured an unrestricted function, it'll construct for us an unrestricted function, right? And again, once we've done that, we can sort of characterize this relationship using qualified types. So here's the type that I would give the application operator. What we say is that it takes an f function from t's to u's and gives back a g function from t's to u's, such that f supports more structural rules than g. So the final constraint I'm introducing today is a sort of greater than or equal to constraint. And that's basically counting the structural rules. A simple example is say that the unrestricted function space is greater than or equal to the linear function space, right? But this isn't just about functions. If we go back to the example I started with, the K combinator, we can see that it has a very similar type, right? We're going to take a T, we're going to give you back a function that doesn't support any more structural rules than T did. If T was Booleans and it supported, contraction and weakening, then our result function from U to T can also support contraction and weakening. On the other hand, if T was linear, then our result can't be linear. So the use of these greater than predicates isn't limited to functions. I want to show you one more thing before I'm done, because you might be saying, all right, fine, functions are complicated, but why do we need to bring in all this qualified types machinery just to talk about functions? Put the complication into functions and move on with your life. The point is, this isn't just about functions. Let's consider a couple of kind of useless existential types. I'm writing them in Haskell syntax, but pick your favorite existential type system. The first one, T1, captures an A. So look at the constructor, make T1, it takes an A, it gives us back a T1. We don't know anything about A. In particular, we don't know whether A is linear or unrestricted. The question is T1 linear or unrestricted? If I give you a T1 value, can you copy it? Of course, the point is you don't know what's in there. It could be a file handle. You're not allowed to copy file handles. So we have to treat T1 values as if they're linear, right? Now consider T2, which is almost as useless, but I've captured one piece of information about the contained type, and that's that it's unrestricted, right? So now what can you do with a T2 value? Well, nothing useful, but you do know that the thing captured inside a T2 is unrestricted. And so you can copy or drop a T2 value, right? So basically we have two types here that differ only in their linearity. And that linearity is a function of how they were constructed. And at this point you ought to recognize the same story I've just been telling you about functions. So you might say, well, what if we want to abstract over this? What if we want to characterize T's in a general way that allows us to either create T1s or T2s as necessary? And we can exactly do that using this class T. So the first thing to look at is the constructor. I'm calling it make T. So make T says, if I have some T thing, little t, then make T will take an A and give you a T. And that should look like the form of both the make T1 and make T2 constructors. But it's going to say that T can't have any more structural rules than A did. So if A is a linear thing, then it kind of has to be a T1 thing, because that one didn't have the contraction and weakening. On the other hand, if it's a unlimited thing, unrestricted thing, then we perfectly well could construct a T2. And we're going to see a similar pattern. We can sort of describe a deconstructor for these things, right? The key point here is that the use of greater than or equal to in make T is exactly the same as the use of greater than or equal to in the typing of lambda. The only difference is that here we can sort of see the types that get hidden in the existential package directly, and so we can sort of write it in the programming language. Okay. So I want to talk a little bit about the context, there's been a ton of work on linear types, and I'm not going to do all of it credit in on this slide. There have been a couple of calculi that sort of have tried to solve this linear functional problem with linear functional programming recently, particularly sort of System F Pop and then ALMS by Tov and Pucella. And in both of these calculi, you see a sort of very nice accounting for the behavior of sums and products and all those sorts of things. It follows this intuition that basically a sum, for example, is only as linear as its arguments, or is only as unrestricted as the sort of component types. So I haven't told you anything about those things. You can do them in Quill, but that's sort of handled in this as well. The real difference between this approach and those calculi, besides the sort of choice of qualified types, is the treatment of functions. There's also this work by Simon and Vashko, which is mostly about session types, but incidentally sort of treats linear functions with a bit of subtyping. Again, the crucial difference between that and this approach is that while subtyping, I think, can handle the K combinator, it's going to have trouble with application, because the application, in application, we sort of need to vary in the input type and use that to determine the output type. There's also been a ton of work on, let's say, uniqueness and usage types, and I'm sort of grouping these together because I think there's the same difference between these and what I'm doing. In both cases, you're sort of trying to figure out how often values are used and use that to sort of determine your compilation strategy or something like that. And I think that means these are basically descriptive systems, right? The key thing is to say, if you figure out that something's used once, that's great, it gives you a benefit. But if you sort of can't compute that well enough, you can always sort of fall back to saying, well, we'll treat it as if it was used multiple times. On the other hand, I'm interested in sort of safety properties where you really don't have that fallback, and that means that the linearity sort of has to be exposed in the programming language instead of being able to be hidden under the surface like you can do with sort of with usage types. Finally, there are a number of things I haven't shown you that are in the paper. I look at session types, give you an example of encoding session types in Quill. The key point there is just to say we haven't given up too much linearity. We can still capture the sorts of things we'd want to do. I also look at monads. So the key thing here is to realize that different monads use their continuations differently, right? State calls its continuation once. So if the continuation, the state computation has captured something linear, that doesn't cause a problem. The exception monad, on the other hand, may not call its continuation at all. And so the continuation in that case had best not capture, something linear. Now you might say, oh no, do we have two different types of monads? Are we sort of going to get back into this world where everything sort of multiplies? But it turns out we don't. We can come up with a nice generalization of monads that works in all these cases. I do a bunch of meta theory, show you sort of principal types and type inference, a type safety property. And in particular, if you give me a term in a sort of simple core functional language, in this case OML of Mark Jones, I showed that it can sort of type in Quill as well. So the basic idea here is to say the types are different. The types in Quill are more refined than the types in sort of traditional intuitionistic functional languages, but the terms are the same. And so anything that has a type, in a nice traditional functional language can be given a type in Quill. And finally, I wanted to say something about my prototype implementation, which you can probably find if you look on common places for these things. But this really isn't, a particular programming language. This is an approach that I think would be valuable in a number of programming languages, basically any place that you think linearity would be useful. So, there is a prototype implementation coming soon, but if you have a different language that you think could benefit from linearity, I think that would be a great application as well. And with that, I'm done again. Thank you for your time. I'll take any questions.
All right, time for questions.
Hi, Derek Dreyer, Max Planck Institute. Can you go back to the last slide? Yeah, right. So I'm just wondering, so you introduced motivated the talk with the ability to write, or the desire to write, functions that are generic in the linearity of one of their arguments. So are these examples, like session types, and I don't know exactly what the examples are, but are they actually exploiting this?
The monads one definitely is, yeah. Because the key point there, right, is that bind wants to be generic in the continuation type. It's actually a little more than that. Because depending on your monad, bind may or may not be generic in its continuation type. But composition or application is sort of a simplified version of composition, and composition falls into that pattern of needing to vary based on its arguments.
Okay, yeah, the reason I ask is because somehow the question you're asking here is very reminiscent of a problem that came up in module system design, trying to develop type systems for higher order functors, and there the canonical example was always the apply functor. So when I saw the beginning of your talk, I was like, I know he's going to talk about the apply function, and because you want to sort of give a a type for that is generic and whether the functor argument is applicative or generative.
Right.
And so there's never like a fully satisfying account of that. And I always thought that was basically because there weren't that many examples. But other than these sort of basic composition operations, that's why I'm wondering if there's a wider range of.
So I guess I would say my examples are all in that sense simple. I mean, they're sort of composition and bind and that sort of thing.
Right.
But my response to the claim that those are simple is to say that they underlie a lot of what makes functional programming attractive. So, if we can't give a satisfying story for composition, we're going to have a hard time, I think, giving a satisfying story for, lenses or functors or any of the things that make modern Haskell fun.
Okay. All right. Any more questions?
Hi, Liam O'Connor, UNSW. I was just wondering, could you compare this to something like Itzko de Vries's polymorphism for uniqueness types, where he annotates the function types with their uniqueness variables and has constraints on them? It sort of seems similar to me.
The crucial difference between this and sort of uniqueness, I think, is this point of whether it's how it's exposed in the language and how that affects the sort of abstractions that we define in the language. So in the case of something like linearity, because it's prescriptive, it really has to, for example, show up in our account of monads. We can't sort of fall back on the sort of non-unique interpretation. We can't fall back on a non-unique interpretation.
But I was referring more specifically to the use of polymorphism to encode we don't know if this function is going to be linear or not unless we know how the linearity of this argument, for example. So this sort of constraint can be expressed by using de Vries's system. So I was just wondering if you'd seen that or if it's similar in any way.
Yeah, I've seen it, and yeah, I think it's similar. But I guess, again, I think sort of in a lot of these systems, what's the other example? So it's useful to have sort of unique and non-unique Booleans, right? I mean, maybe it's not, but you could imagine it being useful to have unique and non-unique Booleans.
Right.
And similarly, it might be useful to have unique and non-unique file handles. I'm sort of saying it's not useful to have, in my system, linear Booleans because I could just write the operations to drop and duplicate them. And it's not useful to have non-unique, non-linear file handles because that violates the safety property. So the sort of view of types is a little bit different than you get with these sort of systems that put these sort of linearity or unrestrictedness modifiers on types.
Okay, I'm not quite convinced, but we can talk offline. Yep. All right.
Jenny Hackett, University of Nottingham. So I like this a lot, but can you go back to class T thing?
Okay.
Yeah, I'm surprised that you have class T rather than some kind of generic data. I mean, if I wanted, let's take a less silly example and say I wanted lists with, I wanted linear lists and unrestricted lists. Would I have to write both of those? Or would I have to write it once and have some magic happen?
I would certainly hope that you could write it once and have some magic happen, right? This is an entirely replicatable pattern. If I were building a compiler, I would build it into the compiler. I'm just trying to show you here that it doesn't rely on compiler-only magic. We can do it just as well on the calculus.
Okay, so does that mean there's not a sort of a there's not a theory behind it? It's just something that the compiler could do.
The treatment of functions is built into the treatment of functions has to be sort of built into the typing rules, but the treatment of everything else can be derived.
Okay.
Right. Time for one quick question. Yeah.
Is it possible to extend your language with dependent types? Sorry, I couldn't help.
So there are people who've looked at linearity in the context of dependent types, and those people are not me. I think if you were to do that, you'd probably need a much more interesting calculus to start with, but you'd probably find similar problems at some point. And so some notion like this sort of relationship amongst types would be useful. But I don't claim to have looked at the interactions with dependency directly.
All right, let's thanks Garrett again.